We have three charges on a number line. And here's our 0 position. And you go this way, you have positive x, and everything's going to be in meters. This way is negative x. One charge is negative 18 microcoulombs here. You have negative 12 microcoulomb charge here at +1, and 24 microcoulomb charge over here at +7. So first, draw free body diagrams for the electric forces acting on the three charges. Then find the magnitude of the forces, first between Q1 and Q2, then Q1 and Q3, and then Q2 and Q3. Then find the magnitude and direction of the net electric force on charge 1, charge 2, and then charge 3. So draw three free body diagrams, one for each of the charges. And what we're going to assume on all of this, because this is electrostatics, is the charges don't move. They're nailed down there for a second, okay? For some reason we've got them stuck there, they can't move, because once the forces start acting on them, that gets to be extremely tricky. So we're not going to do that at all. We just want the initial force when the charges are put there. So we have three separate problems, one free body diagram for each charge. We only have to include the electric force. We're not worried about gravity here, okay? That's how we stated the problem. Let's focus on Q1 first. It's this charge over here. Q1 and Q2, we're just going to worry about the force between 2 and 1. Q1 and Q2 repel each other. They're both negative, so that's a repelling force between them. So Q1 will want to move to the left because of Q2, and that's this right here. So that's the force that Q2 exerts on Q1. And that's what we're saying right here. Now, F21 and F12, well, where's F12? Right over here. This is the force that charge 1 exerts on charge 2. It's trying to push it to the right. So F21 and F12 are an action-reaction pair, so their magnitudes will be the same. There's another charge acting on Q1. This guy right here, Q3. Q3 is positive, Q1 is negative. So Q3, the force that 3 exerts on 1, it's going to attract it to the right. And then of course, what's Q1 doing to Q3? It wants to pull it to the left. But we're not worrying about Q2 and Q3 yet, we just want Q1. So F sub 3, 1, action-reaction pair with F sub 1, 3, so their magnitudes will be the same. Do not worry at all about the sizes of these vectors. We have no idea what's going to turn out yet, so just draw them equal. Not a big deal. The direction is key, however. So Q1 has two electric forces acting on it, F21 due to charge 2 and F31 due to charge 3. We'll label that free body diagram Q1 because the forces are acting on charge 1. And we also have to label the forces, which I think we've already done in the previous two slides, so we're good. Once again, just making the point, because here's our answer. Don't worry about drawing the arrows to scale. You may not know yet which force is larger. The direction is key, not the magnitude. Okay, we've done charge 1. Now let's move over to charge 2. Well, hey, look at this. We already have one of the vectors, because we got that when we were dealing with charge 1. But let's review what's going on. Q2 is repelled from Q1 because they're both negative charges. It feels a force away from Q1 to the right, and F12 and F21 are an action-reaction pair, so equal in magnitude and opposite in direction. There's another force on Q2. Right, here's Q2. Q3. Q3 is positive, Q2 is negative, so Q3 is going to attempt to pull Q2 to the right. So that would be this force right here, the force that 3 exerts on 2. F sub 3, 2 and F sub 2, 3 is also an action-reaction pair, so their magnitudes are the same. Here's our free body diagram at the bottom. All right, looks just like what we drew up there. We have two forces pulling 2Q to the right. One is a repelling force from charge 1, and the other is an attractive force from charge 3. So sometimes you'll have two forces pointing in opposite directions, sometimes they'll point in the same direction. And finally, we'll get to charge Q3. We've already shown this force here. Charge 1, which is negative, is attracting charge 3, which is positive. And these two forces It's an action-reaction pair. They are equal in magnitude and opposite in direction. There's another force on Q3. Okay, Q3 is positive. Here's Q2 negative, so it will attract Q3. So the force of 2 on 3 is to the left. And that just happens to be in an action-reaction pair with the force that 3 exerts on 2, so they will have the same magnitude and different directions. And now we're going to go ahead and label our free body diagram for Q3. Right, just move it from there to there. We label it Q3, why? Because it's Q3, and we have two forces to the left, the force of 1 on 3 and the force of 2 on 3. Find the magnitude of the force between Q1 and Q2. We can use Coulomb's law to solve for the force. So that's KQ1 Q2 over R squared. We find R by finding the distance between the two charges. So it's -9 here, 1. So that distance is 10. Don't include signs on your charges. The question asks for the magnitude of the force. Our free body diagram will tell us the direction of the forces. So we plug in our numbers. Here's K. Here's Q1, Q2. The distance squared, make sure you square the distance. And also microcoulombs has to be converted to coulombs by multiplying by 10 to the -6. And I almost covered it up there. Okay, that's important there, and that's important there. And we get the force between Q1 and Q2 is 0.0194 newtons. Now we need the magnitude of the force between Q1 and Q3. Well, this distance here is 7. This is 9. 9 plus 7, 16. So you can see it here in the denominator, 16 squared. Leave the signs off the charges. And again, remember, microcoulombs, multiply it by 10 to the -6 to get coulombs. And we get the force between 1 and 3 is 0.0152 newtons. And finally, the only pair we're missing now is the force between Q2 and Q3. And what's their distance? Well, this is at 1, this is at 7, so 7 minus 1. The distance between them is 6. Coulomb's law. Here's K, charge 1, charge 2. And again, we have the 24 times 10 to the -6 coulombs because it's microcoulombs. And we get the force is 0.072 newtons. And now, these three forces that we calculated are all part of an action-reaction pair. The magnitudes of these forces are equal, although the directions are opposite. So the force of 1 on 2, the magnitude is the force on 2 on 1. So we got two forces for the calculation of 1. Same thing with 1 on 3, 3 on 1, and 2 on 3, 3 on 2. Now we want the magnitude and direction of the net electric force on Q1. So we go back to the free body diagram, just like in dynamics. Okay, here's our two forces, force of 2 on 1, force of 3 on 1. The net electric force will equal the sum of both electric forces. So here's the force of 2 on 1, the absolute value, and here's the force of 3 on 1. The signs on these forces correspond to the direction of the arrows on the free body diagram. F21, this guy here, is going to be negative. Why? It's pointing to the left. F31 is positive because it points to the right. So we sum our forces here. So we have the positive force, 3 on 1, and the negative, 2 on 1. So that could be written plus or minus F21, but plus a minus force is the same as subtracting. And we get the sum of the forces on charge Q1 is negative 0.0042 newtons. So what does that tell you? The net force is going to push Q1 that way. And now let's look at the magnitude and direction of the net electric force on charge Q2. We look at our free body diagram and see both forces are to the right. So that means both forces, here's our magnitudes here, we'll get a positive value because they're directed to the right. So we have 0.0194 newtons plus 0.072 newtons, add them together, and we get the force, and it'll be to the right because it's positive, 0.0914 newtons. So this charge is going to want to move in this direction. And finally, the magnitude and direction of Q3, the force on Q3. Both forces are to the left. So look at this. Both will have negative values. Here's our magnitudes that we calculated with Coulomb's law. Plug them in, and to no surprise, the sum of the forces will be negative, so Q3 will feel a net force in that direction.